Video will be discussing on the topic of high frequency resistors. In previous video, we have discussed about how does the resistor, inductor and capacitor behaves with respect to frequency, and what is the difference between the excitation that we are going to provide, which is the AC excitation or DC excitation, and based on which how does the actual circuit behaves. So these are the things which we have discussed in our previous videos. So in this video, we'll be discussing on the topic how does actually the resistor behaves in case of the high frequency. So as we have discussed earlier, at 0 hertz, which is the low frequency, or I could also say it as a direct current, the resistor will behave like a ideal resistor, which means it only blocks the flow of current through the circuit. Okay, but when we are moving with the higher frequencies, which is the megahertz or gigahertz, in these frequencies, the resistor is not actually a resistor only. Okay, because of its internal structure and also the leads, that is the connecting part which we are using, no, so those leads also provide some kind of inductance and capacitance, which we actually call it as the parasitic effect. Okay, so in simple terms we could say that whenever we are dealing with the lower frequency, resistor is just an resistor, but when we are dealing with a higher frequency, along with the resistance we also have the inductive and capacitive effect along with it, and in this video we'll be discussing what is the reason for the inductive and capacitive effect. Okay, so starting with the different types of resistors that we use in general circuits, the first one will be the carbon composition resistor, and the second one is the wire wound resistor, third one is the metal film resistor, and fourth one is the thin film resistor. So, since our area of interest is majorly in case of the radio frequency, in case of radio frequency, the most commonly used type of resistor is the thin film chip resistors, which we also call it as the SMD resistor. Okay, that is the one which is commonly used in radio frequency and microwave circuits. The reason for opting this resistor in case of the radio frequency is that the first major reason it is small in size. Since we are dealing with the RF components, we want the size of the components also to be small. Okay, so since it is of smaller size, which is of major interest of our concern, and second one is because of its lower parasitic inductance effect, and its performance is also considerably good in case of the higher frequencies. So because of these three reasons, the thin film chip resistors are generally used in most of the circuits. Okay, and we were discussing that resistors at high frequencies behaves differently, right? But we have to know what is the actual reason, right? As I discussed earlier, at case of lower frequencies, the resistor only behaves like a resistor, nothing other than that. It just blocks the flow of current. But when we are moving with the higher frequency, every resistor will contain its lead wires. It also has its internal spacing, and it also has its metal body, right? These parts will act like a tiny capacitor and tiny resistors and tiny inductance. That is what we call it as the parasitic effect, and these are the unwanted components which majorly affect the working of RF signals. Okay, so while we are discussing about this, whenever we are giving a very high frequency to a resistor, instead of just the resistance, we could just imagine the equivalent circuit of the resistor could be like the image which I have shown in this PPT. We could see that we also have a resistor, we have two capacitance over there and two inductance over there. The term R, which denotes the actual resistor which I am going to connect, which produces a voltage drop. But we could see the two different types of inductance which is available in the circuit. which is nothing but the lead inductance, which is the lead which is connected at the two different ends of the resistor, right? And these resistor leads will behave like a small inductor. So as cases of frequency increase, the inductive reactance also increases. The reason for the increase in the inductive reactance is, we know that XL will be equal to 2 into F into L. So whenever there is an increase in the frequency and increase in the inductance, automatically the inductance effect actually increases. Okay. So that is the reason that, like, two different inductance, which is due to the lead that is connected to the resistor. And we could also see that there are two different capacitors which is available at case of higher frequencies in the equivalent circuit, right? One is CA and another one is the CB. So CA is nothing but the stray capacitance. The reason of its existence is that whenever we have two conducting surfaces which is separated by a specific distance or an air gap, it behaves like a capacitor and it starts storing the electric charge. So because of this effect, there is a stray capacitance which is available at higher frequencies. And I could also see that there is another inductance which is CB, which we can call it as the interlead capacitance. This occurs when the lead of the resistor is placed very close to each other. In the sense, in that case, it also forms a tiny capacitor in the circuit. So instead of just having the resistance value, whenever I move with an higher frequency, I'll be having two different lead inductance, and I also have a stray capacitance and also the interlead capacitance, which is added to the actual resistor, which makes a major change in the working of the circuit. Okay. The next topic that we are going to discuss is that in case of the wire wound resistor. As the name itself indicates, wire wound resistor is nothing but whenever I am winding a wire over a core, that is what you call it as the wire wound resistor. Okay. It generally looks like a spring since it is wounded on a small core, and it also behaves like a coil. So but in case of its equivalent circuit, it becomes more complicated. Since there is a winding, there are chances that additional capacitance and additional inductance could get added at higher frequency, uh, i- along with the actual resistance and the inductance which we have over there. So the additional elements here is the L1, which is actually the inductance of the wound wire, and L2 is here the lead inductance. And the other additional component is the C1, which is the capacitance between the adjacent turns of the windings. Since we have a winding over there, we'll be having a different capacitance between the adjacent turns in the winding. So C1 will denote that, and you can also call it as an internal capacitance, or you can also call it as a stray capacitance, and C2 will be the capacitance between the two ends of the resistor. Okay. Usually when we are comparing C1 and C2, the C1 will be having more capacity, C1 will be smaller when compared to the C2. Okay. So we could also see that the equivalent circuit will be having, along with the resistance, will be having three inductance and two capacitance, which is connected to the actual circuit. Again, it is the one which because of this because of this reason only, we are not using the wire wound resistors actually in RF circuit, because it has a large inductance rather than with the circuit which we have discussed earlier, and along with that it also has larger capacitance, and self resonance may occur easily because of the wire wounding. Because of these reasons, these kind of wire wound resistors are generally avoided in case of the RF circuits that we use. Okay. So next, dealing with a small example, if I consider a 500 ohm metal film resistor, which is of a length 2.5, and AWG is nothing but a standard which defines the thickness of the wire, and stray capacitance of 5 picofarad. In that case, I could define the total inductance. Since I also have a resistor inductance and capacitance which is actually connected to the circuit. If you want to define the impedance of the circuit in a single equation, I could define it using it. Z is equal to J into omega L plus 1 divided by J into omega C plus 1 divided by R, and this equation will predict the resistor behavior at RF frequencies. Okay, so if I substitute all the equations, all the values in the equation, the equivalent circuit, or I could also say that the equivalent graphical representation of the circuit will be like the figure which we have inserted. So at lower frequency, we could see that the graph acts like a ideal resistor which is blocking the amount of current, and the impedance remains approximately constant, and there is no effect of inductance or capacitance. The reason is that since we are dealing with the lower frequencies, as we could see that as frequency increases, the plot gets decreasing to a very larger extent, then start increasing and remains constant. So the second region is what we call it as the capacitive effect, and the third region is what we call it as the inductive effect. So in second region, whenever the frequency start increasing, the stray capacitance starts conducting, and current can bypass through the resistor through its capacitor, and overall impedance decreases and capacitive effect increases. The reason is that we know that whenever frequency increases, the capacitive effect starts getting added to the circuit. So whenever the capacitive effect starts getting added to the circuit, the amount of current flow through the circuit decreases, which means the impedance of the circuit has actually increased. Okay, that is the reason this region is called as the capacitive effect. And the region 2, where we can see a sharp edge which is decreasing, that is what we call it as the self resonance. So at around 20 gigahertz, inductive reactance will be equal to the capacitive reactance, and this point is what we call it as the self resonance. And that point, the resonance will be reaching a very minimum value, and the region 4 is what we call it as the inductive region. And as I'm increasing the frequency, what happens over here is, we know that XL is equal to 2 pi into FL. Therefore resistor will start behaving more like an inductor, and the impedance rises rapidly. And that's all about this video. Thank you.